Welcome to the Deep Dive. This is where we really try to cut through the noise and get straight to what matters. Today, we're plunging into something that's not just evolving fast. It's going through a huge shift. Picture this. The United Nations, right? They've officially declared 2025 as the International Year of Quantum Science and Technology. Now, that sounds kind of formal, but this isn't just a symbolic thing, is it?
No, not at all. It's a really big signal, a global acknowledgement that quantum, it's not just stuck on blackboards or in super advanced labs anymore. This UN declaration, it marks a real shift, moving quantum away from just abstract ideas towards, well, tangible stuff, practical development that's actually going to affect all of us.
Yeah, and that kind of global agreement,
Mhm.
it means something. It suggests quantum is like breaking out. It's coming for your world, right?
Exactly.
Shipping how your data is secured, maybe influencing investments, even how your packages get delivered.
It's true. A UN proclamation like that, it really does reflect a global consensus. It tells us that quantum isn't just for the scientists in white coats anymore. It's really poised to fundamentally reshape industries, societies, everything. And what's particularly fascinating here, I think, is that it's not just symbolic. It's a recognition that quantum computing by 2025 has genuinely transitioned. It's gone from being this purely theoretical frontier to what experts are now calling a burgeoning practical technology. We've sort of moved past what everyone used to call the noisy intermediate scale quantum era, the NISQ era.
Oh, yes, NISQ. We heard that acronym a
We
lot.
did. And now we've really entered what many are calling the middle game of quantum development.
Okay, let's unpack this middle game idea because it sounds important. How does this feel different from, what we've been hearing about quantum for the last few years? What does it actually mean for where the tech is heading?
Yeah, it's definitely more than just a new buzzword. The middle game,
Yeah.
it implies that, okay, the ultimate goal, the end game of a fully fault-tolerant quantum computer, that's not quite here yet, we're not there, but we are in this incredibly critical strategic phase. This is the point where, as some analysts put it, winning hardware and software strategies will emerge and lesser ones will fade.
Right, so like in chess, after the opening moves, when the real strategy kicks in.
Exactly like that. The opening moves are done. Now the really deep strategic plays are happening, the ones that are going to determine the winners and losers, essentially. Foundational decisions are being made right now, like which qubit types will actually scale up efficiently, which software approaches are going to be robust enough, which partnerships are going to drive this towards commercial use. Getting these decisions right, it's absolutely critical. It reminds me a bit of the early internet days. The choices made back then about operating systems or network protocols, they shaped everything that came after.
That makes sense.
Yeah.
So it's less about just proving it can work and more about figuring out how it will work best and who will make it happen.
Precisely. It means real value, tangible value, even if it's incremental at first, is actually within reach.
Yeah.
And that means the time for serious investment, for preparation, for building, it's right now. It's immediate. It's the strategic shift, moving away from just pure academic research towards development that's really driven by commercial goals.
Okay, that clears things up a lot. So our mission for this deep dive then is pretty clear. We're going to sift through all the sources we've gathered, the articles, the research papers, the industry notes, and pull out the most important pieces of knowledge. Our goal is to give you a shortcut, basically, a way to get properly informed about this incredibly complex, fast-moving field. We want to help you understand the rapid progress, get your head around the dual impacts, both the amazing transformations and the potential threats, and give you a real sense of how close we actually are to quantum reality.
Yeah.
Hopefully you'll have those aha moments where things just click.
Exactly. And we know this field can feel, well, pretty overwhelming sometimes, right? Full of jargon, complex physics. So this deep dive, we've designed it specifically to cut through all that, to give you a clear, structured understanding of where quantum computing is right now, why it matters so much, and what you should probably be watching for next. We'll try to balance the big picture summaries with, memorable details, specific examples, so you feel informed, maybe even empowered, but not totally swamped. And one thing that really stands out to me is just how fast this field is maturing. From pure academic curiosity into this arena of intense strategic competition, even with geopolitical stuff mixed in, it really feels like a pivotal moment.
It really does. Okay, so let's dive right into that quantum leap of 2025, this idea of moving from theory to actual utility.
Yeah.
It's huge. Now, to really get where we are now, maybe we need to just quickly look back. For years, we heard about the noisy intermediate scale quantum era, or NISQ. Can you just remind us what that meant, maybe in simple terms, and why 2025 feels like such a departure?
Sure, absolutely. So the EISQ era, let's say roughly 2017 to maybe 2024.
Yeah.
That was defined by quantum computers that had, well, a limited number of qubits. We're talking maybe tens, possibly hundreds. And crucially, they were very, very sensitive to noise. Errors crept in easily from the environment, from imperfect control, hence the noisy part.
Right.
Now, these machines, they were incredibly valuable for research, don't get me wrong. They let scientists explore the basic principles, test out early algorithms, really push the boundaries of what was known, but they were essentially prototypes. I like the analogy of the early combustion engines, the really early ones. They worked, they proved the concept, showed it was possible.
But clunky, unreliable.
Exactly. Clunky, unreliable, definitely not ready for your daily commute, right? NISQ machines were groundbreaking for researchers, yes, but they weren't yet showing broad practical usefulness in a stable, predictable way.
Okay. So 2025 is this inflection point you mentioned. The moment we start moving beyond those noisy prototypes, what does that actually look like in terms of real-world use for, say, a business?
Precisely. 2025 really is marking a significant turning point. It's prompting this whole reevaluation of how we even classify these machines, and it's forcing a strategic shift for the whole field. We're moving out of NSQ and properly into this middle game of quantum development. And the focus has sharpened, really sharpened. This isn't just about changing labels, it's backed by concrete progress. We're seeing advancements that let quantum computers do tasks that are genuinely beyond what classical systems can handle efficiently, even if the quantum computers aren't fully error-corrected yet.
Okay, so actual results, even with imperfect machines.
Yes, actual results. We're seeing businesses in different sectors starting to experiment with quantum-powered solutions and pilot projects, sometimes even in early production environments, and they're starting to see measurable benefits. Tangible stuff. Take drug discovery, for example. Quantum simulations are starting to give more accurate models of how molecules interact than classical supercomputers can manage in the same amount of time. That accuracy boost means fewer expensive, time-consuming lab experiments down the line.
Ah, okay. So real savings, potentially.
Potentially, yes. And if we, connect this to the bigger picture, this shift, it's a massive signal to investors, to business leaders, to policymakers. It's saying, hey, real value is actually within reach now. The time to get serious, to invest, to prepare your workforce, to build quantum readiness, it's immediate. It's this profound reorientation, moving from pure research goals to strategic, commercially driven development. This is where the tough decisions are being made about which technologies will scale, which ones will actually deliver value. It's sorting the serious contenders from the maybe more speculative ventures.
That leads us nicely into the global quantum ecosystem itself, because it sounds like it's incredibly dynamic right now, very competitive. Our sources point to this rapid expansion, especially in the U.S. You mentioned over 24 manufacturers offering more than 40 different quantum processing units, QPUs. That seems like a lot.
It is a lot, and it really points to a maturing market, although, it's still quite fragmented. The U.S. has definitely emerged as a leader, both in terms of processor performance and just the sheer vibrancy of the commercial scene. This explosion of hardware makers, the rise of these regional quantum hubs, it shows how diverse and decentralized quantum innovation is right now. It's not one single path forward. It really does feel like the early days of personal computing. You had Apple, IBM, Commodore, Atari, all these different platforms, different architectures, all competing, all trying to prove their way was best. And that diversity, that competition, it's actually a very healthy sign for a field that's innovating this quickly.
But it's not just competition, right? Our sources also really stress this trend towards more collaboration, that the go-it-alone crowd is getting smaller and partnerships are popping up everywhere. Why is that happening? Especially in areas that sound really expensive and hard, like error correction.
That's a really critical point, and it speaks directly to just how incredibly difficult and capital-intensive scaling quantum tech really is. That go-it-alone approach is just not sustainable for most players anymore. There's this widespread recognition now that the massive technical hurdles, especially things like building robust quantum error correction, they just demand a collective effort. It's too big for one company. And that hardware fragmentation we just talked about, those 40-plus different QPUs, that strongly suggests that no single company is going to own the entire stack. From making the qubits all the way up to the application software, it's just too much.
So interdependence is key.
Interdependence is absolutely key. The ecosystem is forming around this multifaceted approach. Hardware makers, software platforms, application developers, they all have to work together. If you connect it to the bigger picture, this is a really crucial evolution. It signals a shift towards an interdependent future for the industry, not a monopolistic one. It's just too complex, too expensive for one player to dominate everything. The R&D costs, the manufacturing, they're staggering. So now, partnerships, open source projects, they're standard practice. They cover pretty much every phase of quantum development and getting it to market. A great example is the Fermilab-led SQMS Center, the Superconducting Quantum Materials and Systems Center. That's a big collaboration. Government, universities, industry partners all focus specifically on improving qubit performance and advancing U.S. tech leadership by pooling expertise and resources.
And here's where it gets really interesting. It's not just tech companies and universities collaborating. Government's right in the thick of it, too. Our sources mentioned the potential reauthorization of the National Quantum Initiative Act of 2018, the NQIA. That sounds like vital funding, right? Public-private partnership stuff.
Absolutely vital. The original NQIA was foundational. It committed over, $1.2 billion across different federal agencies, providing stable support for quantum R&D. If it gets reauthorized, and it looks likely, that sends a really clear signal of continued government commitment for the long haul. This public-private cooperation is essential. It provides the funding needed for the long-term, really capital-intensive research required to crack some of these remaining engineering nuts. Governments worldwide see quantum as strategic tech now. It affects everything: national security, economic competitiveness, scientific leadership, even the future of things like critical infrastructure. So that kind of sustained long-term funding gives researchers and companies the stability they need to tackle these really ambitious multi-decade projects.
Okay, let's get into the hardware then, because this is where so much of the fundamental action is. You said 2025 isn't defined by one winning technology, but by progress across several competing platforms: superconducting, trapped ion, photonic, neutral atom, and Microsoft's different bet. Can you walk us through these, like how they work, the pros, the cons, and what's new for them right now in 2025?
Definitely. This is really the technology frontier, as you said. Different approaches are making different trade-offs: qubit count versus error rate, gate speed versus how long the quantum state lasts, the coherence time. Understanding these is key. So first up, superconducting qubits. These are the ones companies like IBM and Google are heavily invested in, really pushing for large-scale computation. How they work: basically, they use tiny electrical circuits made from superconducting materials like niobium or aluminum that behave like artificial atoms when you cool them way, way down near absolute zero. At those temperatures, they show quantum properties like superposition.
Near absolute zero. Wow.
Yeah, incredibly cold. Advantages. The big plus is speed. Their gate operations, the basic quantum calculations, are very fast, typically in the tens of nanoseconds. Speed is crucial because quantum states are fragile. You need to do your calculations quickly before the state disappears, before decoherence kicks in. Faster gates mean you can run deeper, more complex algorithms within that short lifetime, which helps manage errors, challenges. But that fragility is their Achilles heel. Their coherence times are short, usually under 300 microseconds. They lose their quantum information fast. And yeah, that extreme cooling, it requires huge, complex cryogenic refrigerators. Very expensive, very difficult to scale up massively. 2025 breakthroughs. We're seeing progress, though. IBM's new Nighthawk processor, for instance, is designed with better connectivity between qubits, allowing for more complex circuits, especially for those hybrid quantum HPC setups. And places like NIST and that Fermilab SQMS Center, they've made real strides in fabrication, things like encapsulating the niobium surfaces to protect them from contaminants. That's pushed coherence times up to around 0.6 milliseconds in some cases, a really significant jump for this tech.
Okay, zero point 0.6 milliseconds. Still sounds tiny, but a big improvement relatively.
It is in the quantum world. That's a long time for these circuits. All right, next. Trapped ion systems. Companies like IonQ and Quantinuum are big players here. They use individual charged atoms ions trapped by electromagnetic fields as their qubits. How they work: they use precisely controlled lasers to manipulate the internal energy states of these trapped ions, defining their qubit states, 0, 1, or superposition. Lasers are also used to cool the ions and to entangle them, linking their fates quantum mechanically. It all happens in an ultra-high vacuum chamber. Advantages: their big strengths are stability and accuracy. They have impressive coherence times, anywhere from, say, 0.2 seconds up to an amazing 600 seconds in some lab settings. And their measurement accuracy is incredibly high, often better than 99.9%. Plus, every ion of the same element is identical, which eliminates manufacturing variations you might get with fabricated circuits.
600 seconds, that's ages compared to microseconds.
It's a massive difference, yeah.
Oh, yeah.
Challenges. Historically, the challenge has been scalability. Designing complex traps to hold and precisely control hundreds or thousands of ions is tough. Moving ions around, targeting them accurately with lasers. It gets incredibly complex as you scale up, and maintaining that ultra-high vacuum is demanding. 2025 breakthroughs. IonQ is tackling scalability head-on. They acquired a company called Oxford Ionics, and they've had a breakthrough using synthetic diamond materials. The key here is that these quantum-grade diamonds can apparently be mass-produced using standard semiconductor chip-making techniques. That's potentially huge for making scalable, founder-compatible quantum systems and networks using existing industrial infrastructure.
Interesting. Using existing chip factories. That could be a game changer. Okay, what about photons? Light particles as qubits.
Right, photonic quantum computers. Players here include Quandela and Sequantum. They use individual photons as their qubits, how they work. Quantum information gets encoded into properties of the photons, like their polarization, the direction their electric field oscillates, or maybe just their presence or absence in a particular path. Interactions between qubits happen using optical components like beam splitters, phase shifters, often all integrated onto a chip. Advantages. A massive advantage is they can operate at room temperature, at least the core processing part. No need for those giant, expensive refrigerators. That makes them potentially much more practical and easier to scale in some ways. Also, photons don't interact strongly with their environment, which gives them an inherent resistance to decoherence. They're naturally quite robust.
Room temperature sounds very appealing.
It really does. Challenges. The flip side is that generating single photons on demand, manipulating them precisely, entangling them, and then detecting them reliably and efficiently, especially when you need lots of them. That's a major engineering hurdle. Getting photons to interact strongly enough to perform gates can also be tricky. 2025 breakthroughs. The big news here is integration. Researchers have managed to cram all the complex optical bits, tiny lasers, micro-ring resonators, waveguides, onto a single photonic chip, maybe just a centimeter square. This kind of integration is crucial for making portable, scalable devices that could eventually be mass-produced.
Okay, integrating all the optics. That makes sense. And then there's neutral atoms.
Yep, neutral atom architecture. Companies like Pascal and Quera Computing are known for this. They use neutral atoms without an overall electric charge held tightly in place by highly focused laser beams, often called optical tweezers. How they work. They cool the atoms way down, then trap them in these arrays of laser tweezers, often in 2D or even 3D patterns. The internal energy states of the atoms serve as the qubits. To get the atoms to interact and entangle, they often excite them to high-energy Rydberg states, which makes them interact strongly over relatively large distances.
Optical tweezers.
Yeah.
It's all science fiction.
It kind of does. Advantages. They also operate with room temperature control systems, although the atoms themselves are very cold.
Right.
They have great potential for scaling. People are talking about trapping thousands of atoms. They offer high connectivity, meaning a qubit can potentially interact with many others around it. And like ions, you get perfectly identical qubits because every atom of, say, rubidium is the same as every other rubidium atom. Quora's Aquila system already has 256 atoms, which is impressive. Challenges. Controlling individual atoms precisely in these large arrays is demanding, and the speed of their quantum gates tends to be slower than superconducting qubits, which could be a limitation for some algorithms. 2025 breakthroughs, we're seeing real utility demonstrated. That Pascal collaboration with Qubit Pharmaceuticals, analyzing protein hydration, that's a great example. They're using a quantum algorithm for a really critical task in drug discovery, figuring out exactly where water molecules sit around a protein, which affects how drugs bind. It's the first time a quantum algorithm has been used for that specific, complex task.
Wow. So practical applications are starting to emerge there, too. And finally, Microsoft's big bet, the topological one.
Right, Microsoft's topological bet. This one is different. It's definitely high risk, but potentially very high reward. How they work. They're trying to use these exotic things called Majorana zero modes. These aren't fundamental particles. They're more like collective behaviors, quasi-particles, that can emerge in certain materials under specific conditions. The idea is to encode quantum information not in the state of a single particle, but in the way these Majoranas are arranged or braided around each other.
Braiding, okay, this sounds really abstract.
It is very abstract. Advantages. The potential payoff is huge. Because the information is stored non-locally in this topological property, it should be inherently protected from local noise and errors. It's like the information is smeared out and can't be easily disrupted by a small disturbance at one point. If it works, they could potentially bypass many of the really hard scaling challenges related to error correction that other approaches face. They might need far fewer physical qubits to make one stable logical qubit. challenges. The massive challenge has been actually creating and verifying these Majorana modes reliably in the lab. It's been extremely difficult, requiring very specialized materials, ultra-low temperatures, and incredibly precise measurements. There's been a lot of debate in the scientific community about whether they've truly been observed unambiguously. 2025 breakthroughs. The big news was Microsoft unveiling its Majorana 1 processor back in February 2025. They claim it's the world's first chip based on topological qubits. This is a major milestone for them, a step towards proving the viability of this radical approach, if they succeed in the long run. Well, it could completely change the game in the hardware race.
Okay, that is an incredible range of innovation happening all at once. It really does sound like there's no single clear winner yet. Maybe the best tech depends on the specific problem, or maybe, like you said, it'll be some kind of hybrid approach that ultimately delivers. For you listening, the takeaway seems to be, don't bet on just one horse in this race. It's more about understanding the different strengths and weaknesses and seeing how they might combine to create the quantum reality that solves your kinds of problems. It still feels a bit like the Wild West of quantum hardware, doesn't it? Anything feels possible. So with all these different hardware options bubbling up, you have to wonder how the big tech players are placing their bets. I mean, these companies are pouring billions into this. Their strategies, their roadmaps, they're going to massively influence how quickly this all develops and in what direction. Let's start with Google. Their approach seems very force-focused, maybe even academic. A specific step-by-step quest.
Yeah, Google's strategy is definitely highly focused, and you could say academic in its rigor. They've laid out this clear 6-milestone technical path, and the ultimate destination is unambiguous. A large-scale, error-corrected, fault-tolerant quantum computer. Their roadmap really emphasizes cracking the code on error correction above everything else. They seem willing to prioritize getting that fundamental physics and engineering right, even if it means delaying near-term commercial applications or utility.
So less focus on immediate profits, more on building the perfect machine first.
That seems to be the philosophy. It's an approach that resonates strongly with the academic and deep research communities. They're aiming for this monumental leap, this foundational achievement, rather than taking smaller, incremental steps towards commercial value right now. The gamble, I suppose, is that building that truly robust, theoretically sound, fault-tolerant machine first will ultimately be the most valuable path in the long run, even if it takes longer to get there. It's designed for massive scalability and reliability from the ground up.
It's like they're meticulously building the perfect fully insulated house, foundation first, brick by brick, rather than, say, moving into a couple of functional rooms while the rest is still under construction. So what are these key milestones they've set out?
Right. Well, I've already ticked off the first two. Milestone 1 was beyond classical. They hit that back in 2019 with their Sycamore processor. That was the famous quantum supremacy experiment, where they did a specific calculation in about 200 seconds that they estimated would take the world's most powerful classical supercomputer, like 10,000 years. That really kicked off the NISQ era discussion in earnest.
Right, the supremacy claim. That caused a stir.
It certainly did. Then, milestone 2 was quantum error correction. They achieved that in 2023. This was huge. They demonstrated a logical qubit prototype, basically. They showed experimentally that you could actually reduce errors by encoding information across more physical qubits using a quantum error correction scheme. It proved the basic principle could work in real hardware, taking QEC from theory towards practice.
Okay, so they proved error correction works in principle. What's the focus now in 2025 and looking ahead?
So right now, Google is squarely focused on milestone 3, building a long-lived logical qubit. This is a massive engineering lift. The goal here is to create a single logical qubit that can survive for potentially 1 million computational steps with less than one error occurring during that whole time.
1 million steps with less than one error? That sounds incredibly difficult.
It is incredibly difficult. It requires major improvements across the entire system, better physical qubit performance, scaling up the hardware architecture, refining the error correction techniques themselves to an unprecedented level of precision. This is really the bedrock of their whole fault-tolerant vision. If they can crack this, it's a giant leap. After that comes milestone 4, which is creating a logical gate. You need reliable gates to actually manipulate these logical qubits and do computations. Then milestone 5 is engineering scale up, getting to maybe 100 reliable logical qubits working together. And the final goal, milestone 6, is the large error-corrected quantum computer. They're talking about potentially 1 million physical qubits supporting maybe the 1,000 logical qubits with an incredibly low logical error rate, something like 10 to the minus 13. And they're targeting this for around 2029.
2029, that's ambitious.
Very ambitious. But that's Google's grand vision, a clear, methodical path towards what could be an almost perfectly reliable quantum machine capable of running algorithms we can barely even imagine today. For you, this is the blueprint for a future where quantum computers operate with incredible precision. Now, in really stark contrast to Google's sort of foundational long game approach, you have IBM. They're pursuing what they explicitly call a utility first roadmap. Interestingly, they also seem to be converging on a 2029 target for their fault-tolerant quantum computer. They call theirs the IBM Quantum Starling. But the path they're taking to get there, it's dramatically different from Google's. IBM's roadmap, which they updated just recently in June 2025, actually targets demonstrating quantum advantage, meaning real, tangible utility where quantum outperforms classical by the end of 2026. So well before they expect full fault tolerance.
Okay, wait. So both aiming for fault tolerance around 2029, but IBM wants to show practical value much sooner. This raises an important question. How do these different strategies affect things for people looking to use quantum now? Does it change the timeline for when you might actually see benefits?
That's exactly the question. And it highlights a critical difference in business model innovation. IBM's strategy is all about bridging that gap between the cutting edge research and actual commercial viability much, much sooner. They have this core belief that quantum computing won't initially replace classical computers entirely. Instead, they see it first serving as a specialized accelerator for classical high performance computing, for HPC systems.
Ah, okay. So working with classical, not against it.
Precisely. This approach lets them demonstrate tangible commercial value to their clients along the way. They're actively trying to create a quantum as a service market now, building an ecosystem of users who are already learning how to leverage quantum resources, even imperfect ones. They're essentially proving the value proposition step by step, making quantum a more immediate, usable tool, even while it's still noisy and intermediate scale. It's a very different philosophy than Google's wait for perfection approach. IBM's path might get useful results into users' hands faster, while Google's might deliver a more powerful universal machine later on.
So it really is like adding that turbocharger to your existing supercomputer, like we said earlier, not waiting to buy a whole new type of car. It's about enhancing what's already there.
Huh.
What are IBM's key steps? There are milestones for delivering this more immediate utility.
Exactly. Well, a key enabler is their Nighthawk processor, which came out in 2025. It's specifically designed with higher connectivity between qubits. That lets it run more complex circuits, which is crucial for exploring these first real-world quantum advantage use cases. And IBM is putting huge emphasis on tight integration with HPC. We're seeing collaborations pop up like the one between quantum machines and NVIDIA. They debuted the DGX quantum system in March 2025.
DGX Quantum, what's special about that?
It's basically a specialized NVIDIA system that tightly integrates a classical AI supercomputing chip with a quantum control system. The key is the latency, the delay in communication between the classical and quantum parts. They have achieved incredibly low latency, reportedly sub 4 microseconds for a round trip.
4 microseconds. That's insanely fast. Why is that so important?
It's vital because many promising quantum algorithms, especially these near-term ones, actually need to constantly talk back and forth with a classical computer. The quantum part does a calculation, sends results to the classical part for processing or decision-making, which then tells the quantum part what to do next. If that communication is slow, the whole advantage disappears. So low latency makes quantum a true integrated accelerator within an existing HPC workflow. IBM's technical milestones for 2025 involve really pushing algorithms that combine quantum and HPC and also demonstrating robust error correction code, even if not full fault tolerance yet. This path involves a series of new modular quantum processors. They've announced names like Loon, Kookaburra, and Cockatoo, which are stepping stones towards that ultimate Starling system. Starling, by 2029, is planned to run maybe 100 million quantum gates on 200 logical qubits. And IBM has a pretty rigorous definition for fault tolerance. They say it must be universal, adaptive, and modular. Universal means it can run any quantum algorithm. Adaptive means it can adjust to changing conditions or errors. And modular means it can be built from standardized interconnected units. So for you, the message from IBM is very much about how quantum can start adding value today or very soon by working alongside your existing systems, not just as some far-off dream machine.
Okay, so Google and IBM have these ambitious but quite different roadmaps. But they're not the only giants in the game. What about Microsoft? They took this really unique path, didn't they? High risk, high reward with those topological qubits.
That's right. Microsoft is playing a different game altogether. They're making this significant long-term bet on topological qubits. Their Majorana 1 quantum processing unit, which they showed off in February 2025, is supposedly the world's first chip built using these exotic quasi-particles. As we touched on, topological qubits are pursued because they're thought to be inherently stable. The physics behind them is meant to naturally protect them from errors. The quantum information isn't stored in one tiny spot, like a single atom spin, but it's encoded in these non-local properties of the whole system. That makes them theoretically much less sensitive to local disturbances or noise.
And why is that so significant? How does that inherent protection help with the scaling challenges everyone else is fighting?
Well, and it's still a big if, but if this high-risk strategy pays off, it could be revolutionary.
Huh.
Because they're inherently protected, topological qubits might need far less overhead for error correction compared to other types. Think about it. If you need, say, 1,000 physical superconducting qubits to make one stable logical qubit, maybe with topological qubits you only need 10, or maybe even fewer. That could drastically reduce the sheer number of physical components needed to build a powerful, reliable quantum computer, potentially bypassing some of the biggest scaling roadblocks.
Wow, okay. That would change everything.
It would. It could completely alter the hardware race. Of course, the challenge has been proving it works reliably. But Microsoft is also hedging its bets a bit by leveraging Azure Quantum. That's their cloud platform. It's designed to be hybrid, offering access not just to their own potential topological hardware, but also to hardware from partners, like neutral atom systems from Atom Computing. So they're making quantum experimentation accessible via cloud, regardless of the underlying qubit type.
Smart. And speaking of cloud giants, Amazon Web Services, AWS, they didn't want to be left out, right? They actually jumped into the hardware race themselves in 2025.
Yeah, AWS made a big move. They debuted their own chip called Ocelot in 2025. It uses a different approach to error correction called bosonic quantum error correction, specifically using something called cat qubits.
Cat qubits, like Schrodinger's cat.
Kind of, yeah. The name comes from that famous thought experiment. Unlike a simple qubit with two states, 0 and 1, a cat qubit encodes information using a superposition of two distinct macroscopic states of light or microwave field states that are as different as possible, like the cat being alive or dead. This inherent difference makes them more resistant to certain kinds of errors, particularly bit flip errors. AWS claims this approach could reduce the overhead needed for error correction by maybe as much as 90% compared to some other schemes. So it's another strategy aimed at tackling that core error problem.
Another angle on error correction.
Yeah.
Interesting.
And AWS is also continuing to expand Amazon Bracket, their cloud quantum service. They added a 54-qubit superconducting processor from a company called IQM, giving users even more hardware choices through a single interface. Plus, AWS made a significant investment, was it $36.7 million in IonQ, the trapped ion company. So they're clearly interested in multiple modalities, and ensuring cloud access remains central to quantum development. These tech giants are bringing absolutely immense resources, hitting the quantum problem from all sides.
It's definitely not just Google and IBM anymore. It's not just the U.S. giants either, is it? We hear about other innovators making big strides.
Oh, yeah.
IonQ targeting 100-qubit systems, and China's Zhuangzi 3, 105 qubits, and outperforming supercomputers by a factor of 1,000,000. That sounds incredible.
It really is staggering. IonQ setting goals like 100-qubit systems by 2025 shows the pace of progress in trapped ions. And yes, the reports about China's Zhuangzi 3 system, also based on superconducting qubits, achieving 105 qubits and demonstrating that massive speedup over classical supercomputers for a specific sampling task. It highlights the global nature of this race and the rapid advancements happening worldwide. This whole environment, with all these different players and approaches, is driving what we call convergent innovation. Multiple paths are being explored towards similar goals. And this is having a direct impact on investment trends. We saw a noticeable surge in corporate investor interest in quantum computing startups in the first half of 2025. Funding rounds actually surpassed the peaks we saw back in 2023.
Really? After maybe a bit of a cool down, the money is flowing back in. What's driving that renewed investment? Is it focused differently this time?
It seems to be yes. There's been a definite shift in where the investment is going. A couple of years ago, a lot of the hype and funding was around quantum software companies. Now, in H1 2025, we saw a much greater emphasis on hardware development and also, interestingly, on post-quantum cryptography, the security side.
Ah, okay. So investors are betting more on the foundational tech and the security solutions needed.
Exactly. This shift really signals growing investor confidence that the underlying hardware technology is maturing. It suggests a belief that we're moving past the purely theoretical phase and into a period where the fundamental building blocks, the qubits, the control systems, are becoming viable enough to warrant serious capital infusion for scaling and commercialization. And when you see high-value exits like IonQ acquiring Oxford Ionics for reportedly $1 billion, that sends a powerful message. It confirms that this is becoming a maturing market with the potential for significant financial returns. These aren't just speculative science projects anymore. The core tech is moving firmly into a phase where tangible commercial success seems much closer.
Okay, so we've got this incredible buzz, maturing hardware, shifting investments. But what does this all actually mean? For your daily life, maybe your industry, or just the future of science? We've seen the progress, the strategies. Now let's talk about the impact. The huge potential of quantum open to solve problems that are just impossible for classical computers today. This is where it gets really exciting, right? Moving from theory to actual high-value applications that could genuinely change our world.
Absolutely. The transformative promise of quantum computing, we're really starting to see it take shape now in several key areas. These aren't just hypotheticals anymore. They're high-value, early applications demonstrating real potential, even with today's machines. First, a huge one is accelerating scientific discovery, especially in fields like drug development and materials science. Think about it. Molecules, materials, they behave according to quantum mechanics at their core. Classical computers really struggle to simulate these complex quantum interactions accurately. They often have to use approximations, which leads to a lot of expensive, slow trial and error in the lab.
Right, trying to model reality with tools that don't quite capture it.
Exactly. But quantum computers, they speak the same language. Using algorithms like the variational quantum eigensolver, VQE, they can simulate molecular behavior with potentially much higher precision. This could dramatically speed up the discovery and development of new drugs, new catalysts, new materials with specific properties, basically by allowing researchers to understand and predict molecular behavior far more accurately before they even step into the lab.
Any concrete examples of this happening now?
Yes. That Pascual collaboration with Quibit Pharmaceuticals we mentioned earlier, that's a prime example. They're using a hybrid approach combining quantum and classical computing to analyze protein hydration. Figuring out precisely where water molecules cluster around a protein target is critical for understanding how a potential drug molecule will bind to it. This is a notoriously difficult calculation for classical computers, but they're now deploying a quantum algorithm specifically for this crucial task. It's literally the first time a quantum algorithm has tackled this specific molecular biology problem. It really validates that utility-first idea and shows how quantum could genuinely reshape healthcare by cutting R&D costs and timelines for new medicines.
That's amazing. Okay, what else? Finance seems like a prime candidate.
Definitely. Revolutionizing finance is another big one. The financial sector is widely expected to be an early adopter. Why? Because they deal with incredibly high-value problems that are also computationally very intense, and they're always looking for an edge.
Like portfolio optimization, risk analysis.
Exactly. Things like maximizing portfolio returns while minimizing risk, assessing credit risk more accurately, pricing complex derivatives. These are huge computational challenges. Quantum algorithms, like quantum amplitude estimation, QAE, offer a potential advantage. QAE can, in theory, replace or augment things like Monte Carlo simulations, which are used everywhere in finance for risk modeling and pricing. The potential is to get more precise estimates faster, maybe even using less input data. That translates directly to better, faster financial modeling.
And are banks actually doing this?
Yes, major players are actively exploring it. JP Morgan Chase, for example, has been public about using quantum algorithms to try and optimize their investment portfolio management. They're looking for improved accuracy and efficiency in how they allocate capital. Even small improvements in these areas can mean huge returns when you're dealing with vast sums of money. Finding those optimal strategies faster than competitors is a massive driver.
Makes sense. What about AI? Everyone's talking about AI. Can quantum help there?
Oh, absolutely. Boosting artificial intelligence, AI, is another key area. Quantum computing could act as a powerful accelerator for certain AI tasks, especially for training very complex machine learning models.
How so?
Well, many machine learning tasks boil down to complex optimization problems or processing vast amounts of data to find patterns. Quantum algorithms, particularly in areas like quantum machine learning, QML, show theoretical promise for speeding up tasks like pattern recognition, data clustering, and optimization, potentially offering exponential speedups over classical methods for certain types of problems, especially with large, high-dimensional datasets.
So faster training for complex AI.
Potentially, yes. Think about training the AI needed for fully autonomous vehicles. That involves processing immense data sets from sensors, learning complex driving behaviors. Classically, this can take weeks or even months on the biggest supercomputers. Quantum algorithms might dramatically shorten that training time. And we're already seeing synergy, that DGX quantum platform we talked about. It's not just about low latency, it's also demonstrating how AI can help run the quantum computer better, like using AI for real-time calibration and optimization of the quantum device itself. So it's potentially a two-way street. Quantum boosting AI and AI boosting quantum.
Symbiotic relationship.
Yeah.
Cool. What about more physical world problems, like logistics?
Right. Optimizing logistics and transportation. This is a classic application area because quantum computers, particularly approaches like quantum annealing, are naturally suited for solving complex optimization problems. Many logistics challenges suffer from what's called combinatorial explosion. The number of possible solutions just grows astronomically, making it impossible for classical computers to check them all.
Like the traveling salesman problem,
Yeah.
finding the shortest route.
Exactly like the traveling salesman problem or vehicle routing, scheduling deliveries, optimizing supply chains. Quantum algorithms like quantum annealing or the quantum approximate optimization algorithm, QAOA, could potentially find better solutions much faster than classical methods. Think about calculating the optimal routes for a massive fleet of delivery trucks in real time, minimizing fuel, avoiding traffic, ensuring faster deliveries. For companies like Amazon or FedEx, even small percentage improvements in efficiency here could translate into enormous cost savings and profit increases. This is a prime area for demonstrating early commercial value, likely using quantum as a specialized accelerator for these specific, intractable optimization tasks.
Okay, so drug discovery, finance, AI, logistics,
Yeah.
those are huge.
Right.
Are there other impacts bubbling up?
Definitely. The impact is broader still. We're seeing advances in quantum sensors, which use quantum effects to measure things like magnetic fields or acceleration with incredible precision. This could lead to breakthroughs in medical diagnostics, maybe detecting faint signals from the brain or heart, or even early signs of disease at the cellular level. It could also lead to navigation systems that work deep underground or underwater, independent of GPS. Then there's quantum networks, aiming for truly secure communication using principles like quantum key distribution, QKD. The idea is that the laws of quantum physics guarantee that if someone tries to eavesdrop on the key exchange, the very act of measuring disturbs the quantum state, immediately alerting the sender and receiver. We're also seeing benefits from the integration with HPC, like those IBM AMD collaborations, and the convergence with AI yielding things like potentially more accurate real-time climate modeling. There are sustainable applications too, designing more efficient catalysts for green energy production, optimizing energy grids, maybe even tackling global challenges like carbon capture. And don't forget the broader economic benefits creation of entirely new jobs, new industries, and ironically enhanced cybersecurity through things like QKD, even as quantum computers threaten current methods.
Wow.
Mm.
It's an almost overwhelming list of potential positives.
Yeah.
It really does sound like quantum could touch almost every aspect of technology and society. But
Hmm.
and there's always a but, isn't there? As you mentioned, this incredible promise comes bundled with a pretty profound challenge, a shadow side. We have to talk about the darker implications specifically, the existential threat quantum computers pose to the encryption that protects almost everything online today. And this isn't some distant sci-fi problem anymore, is it? Our sources are framing this as a really pressing security issue right now in 2025. Here's where it gets really interesting, but maybe not in a good way.
You're absolutely right. It's the flip side of the quantum coin, and it's incredibly serious. The core issue is this phenomenon often called harvest now, decrypt later.
Harvest now, decrypt later. Explain that.
It means that malicious actors, and we're often talking about sophisticated nation states with long-term strategic goals, are believed to be already stealing and storing massive amounts of encrypted data today. Data protected by current standards like RSA and ECC, they can't decrypt it now. But the fear is that they're hoarding it, waiting patiently for the day when a sufficiently powerful quantum computer, a cryptographically relevant quantum computer, or CRQC, becomes available. Once they have that CRQC, they can potentially go back and decrypt all that stored data years after it was intercepted.
Oh, wow. So secrets stolen today could be exposed 10, 20 years from now. It's like a ticking time bomb embedded in today's secure communications.
Exactly. Think about the implications. Long-term government secrets, sensitive corporate intellectual property, critical infrastructure plans, even personal health records or financial data that needs to remain confidential for decades. All of it could be vulnerable retroactively. This creates this unique and dangerous kind of security debt. Organizations, governments, individuals, we're accumulating risk right now for data that needs long-term protection. That's why you hear security experts, government agencies, people at CISA, NSA, calling this a national security imperative, and why 2025 feels like a critical tipping point. Huh. Not because the CRQC will arrive in 2025, most experts don't think that's likely, but because the transition to quantum-safe encryption is a huge, complex undertaking that takes many years. We have to start that transition now to be ready before Q-Day, the day a CRQC arrives.
And the reason a quantum computer can do this, the mathematical weapon, is Shor's algorithm, right? Developed way back in the 90s.
Yes, that's the key. Peter Shor, a brilliant mathematician, developed this algorithm back in 1994. And what Shor's algorithm does is find the prime factors of large numbers exponentially faster than any known algorithm running on a classical computer.
And our current encryption relies on factoring being hard.
Precisely. Widely used public key crypto systems like RSA and elliptic curve cryptography, ECC, base their security on the assumption that it's computationally infeasible for classical computers to factor the large numbers used to generate the public and private keys. But a sufficiently powerful quantum computer running Shor's algorithm blows that assumption out of the water. Estimates suggest it could break a standard RSA 2048-bit key, which protects vast amounts of internet traffic and data today, potentially in a matter of hours, maybe even less depending on the machine specifics. That would render all communications and data protected by it completely transparent.
Hours. Okay, that's terrifying.
Cool.
This raises an important question, though. How powerful does this quantum computer actually need to be? How many qubits are we talking about to break RSA 2048? We hear different numbers, and it gets confusing.
Yeah, it's a really important question, and the answer is nuanced and has evolved over time. You often hear the number 4,099 logical qubits cited. That comes from a theoretical paper, I think, by Michelle Mosca and colleagues back around 2003. But that's logical qubits, remember, those perfectly error-corrected abstract units. The real question is, how many physical qubits, the noisy ones we actually build, do you need to encode those 4,099 logical qubits reliably?
Right, the overhead for error correction.
Exactly, and the overhead is potentially massive. More recent detailed analyses, like work by Craig Gidney and Martin Eckrow in 2021, take into account more realistic assumptions about gate speeds, error rates, and specific error correction codes. Their estimates suggest you'd need something more like 20 million physical qubits to break RSA 2048 in about 8 hours.
20 million? Okay, that's a vastly different number than 4,000.
It's a huge difference. And it highlights why predicting the arrival of a CRQC is so hard. It's not just about hitting a certain qubit count. It's about qubit quality, connectivity, error rates, clock speed, the efficiency of the error correction code used. All these factors play a role. So the timeline for a CRQC is definitely a moving target, influenced by ongoing hardware improvements, but also by potential breakthroughs in algorithms or error correction techniques. This very unpredictability, combined with that harvest now, decrypt later threat, is precisely why the migration to post-quantum cryptography, PQC, is considered so urgent. You can't afford to wait until the threat is right at your doorstep.
And this threat isn't just for emails or websites, right? What about things like blockchain and cryptocurrencies?
Absolutely. They face significant risks, too. Most cryptocurrencies, like Bitcoin and Ethereum, rely heavily on ECC for generating public and private keys and signing transactions. A CRQC running Shor's algorithm could potentially break the security of existing wallets, allowing attackers to steal funds. This is prompting serious efforts within the blockchain community to research and implement quantum-safe cryptographic upgrades.
Okay, so the threat is real, the timeline is uncertain but possibly approaching. Which brings us back to the core technical challenge underlying all of this, overcoming the noise. Dealing with quantum errors, you called it the Achilles heel earlier. It really is the central problem, isn't it?
It is, fundamentally. The single biggest hurdle on the path to building truly useful, large-scale, fault-tolerant quantum computers is this constant, relentless battle against noise and decoherence. Quantum states are just incredibly fragile. Any tiny interaction with the outside world, a stray magnetic field, a bit of heat, even imperfections in the control signals can cause the delicate quantum state, the superposition, the entanglement, to collapse or drift. This introduces errors into the computation.
And more qubits doesn't necessarily help.
Not on its own, no. In fact, just adding more noisy physical qubits without a way to manage the errors just makes the overall system noisier. The error rate tends to grow with the system size if you don't actively combat it. That's why scalable quantum error correction, QEC, is so critical. It's often called the defining challenge for the entire field. QEC is the essential toolkit we need to bridge the gap between today's noisy, error-prone devices and the reliable, fault-tolerant quantum computers of the future. Without effective QEC, complex quantum algorithms simply won't run correctly.
But, as we discussed, there is real progress being made on QEC in 2025. Right? It's not an impossible dream anymore.
Significant progress, absolutely. Google's 2023 result was a landmark because it took QEC beyond the theoretical to the practical. They experimentally showed that by encoding information across multiple physical qubits using a specific QEC code, they could actually reduce the logical error rate compared to the underlying physical error rate. They proved the principle works. And we're seeing steady improvements in the building blocks, too. The work at Fermilab's SQMS Center and NIST on improving qubit coherence, getting those superconducting qubits up to 0.6 milliseconds, that's crucial. Better physical qubits make QEC much more efficient. You need less overhead if your starting components are less noisy. These improvements come from really detailed work on optimizing qubit designs, using better materials, and refining the nanofabrication processes, like that idea of encapsulating the niobium surfaces to shield them from noise sources.
So it sounds like it's not just a fundamental physics problem anymore, but a massive engineering challenge across many disciplines.
Exactly. The battle against noise isn't just about quantum physics. It's a deeply complex, multidisciplinary engineering challenge. It involves advanced material science to create better qubits in cleaner environments. It requires incredibly high precision fabrication techniques at the nanoscale. And it demands extremely tight integration between the quantum hardware and the classical control systems. Remember that sub-4 microsecond latency achieved by the DGX quantum. That kind of high-speed classical processing is essential for QEC to work in real time. The classical system needs to constantly measure error syndromes, decode them, and apply corrections to the qubits extremely quickly without introducing more noise itself. Mastering these multifaceted engineering challenges across materials, fabrication, control systems, algorithms, software across every layer of the technology stack, that's really what the next decade of quantum development is going to be defined by. It's about turning these amazing quantum phenomena into reliable, controllable engineering reality.
Okay, so given that huge potential threat to our current encryption, the harvest now, decrypt later problem, Shor's algorithm, it's crystal clear we can't just sit around and wait for Q-Day to happen. There has to be a proactive response, right? A global effort to secure our digital world before it gets broken. And this is where the U.S. National Institute of Standards and Technology, NIST, really seems to have taken the lead.
Absolutely. NIST has been playing a crucial leadership role in coordinating the global effort to develop and standardize new cryptographic algorithms that are resistant to attacks from both classical and quantum computers. This whole field is generally called post-quantum cryptography, or PQC. The goal is to create replacements for the vulnerable public key systems like RSA and ECC that we rely on today for things like secure websites, HTTPS, digital signatures, and secure communication. PQC algorithms are based on entirely different mathematical problems that are believed to be hard even for quantum computers to solve.
So different math problems that Shor's algorithm just
Yeah.
can't touch.
That's the idea, yes. Instead of relying on the difficulty of factoring large numbers or computing discrete logarithms, which Shor's algorithm is good at, PQC candidates often rely on problems from areas like lattice-based cryptography, code-based cryptography, hash-based signatures, or multivariate polynomial cryptography. These mathematical structures seem resistant to known quantum algorithms.
And NIST has been running a big process to select these new standards.
A massive process, yeah. It's been a multi-year, multi-round international competition, really. They solicited proposals for PQC algorithms from cryptographers all over the world, subjected them to intense public scrutiny and analysis, and have been gradually narrowing down the candidates. It culminated, importantly, in August 2024, when NIST published the final versions of the first three PQC standards, Crystal's Kyber for key establishment, and Crystal's dilithium and Sphinx Plus for digital signatures. That was a huge milestone, the first official, standardized, quantum-resistant algorithms ready for deployment.
And this isn't just a U.S. thing, right? It's global. Although you mentioned China's doing its own thing now.
It's definitely a global effort. NIST's process involved researchers worldwide. But yes, it's also becoming a geopolitical issue. Recognizing the strategic importance of cryptographic sovereignty and national security, China launched its own independent push for domestic PQC standards in the first quarter of 2025. This really underscores the urgency nations feel to get this right. And NIST's work isn't done. They're actually holding their 6th PQC standardization conference in September 2025. This shows it's an ongoing process, continuing to analyze the existing standards, develop new ones, especially for digital signatures, and refine everything based on the latest research. They're trying to stay ahead of the curve.
And I heard NIST even created different security levels for these PQC algorithms. What's that about? Sounds like choosing different locks for different doors.
That's a perfect analogy. NIST defined 5 distinct security levels, level 1 through level 5. These levels are designed to offer roughly equivalent security strength against classical attacks as existing standards, like AES 128, level 1, AES 192, level 3, and AES 256, level 5.
AES. That's the standard for symmetric encryption, right? The stuff that's generally considered quantum safe already.
Correct. AES uses symmetric keys and isn't directly vulnerable to Shor's algorithm in the same way public key crypto is. Grover's algorithm, another quantum algorithm, could theoretically speed up attacks on AES, but the generally accepted solution is just to use longer keys, like AES 256, which is already common practice. So NIST is using AES strength as a familiar benchmark for the PQC algorithms. This tiered approach, levels 1 to 5, allows organizations to choose a PQC algorithm that offers an appropriate level of security for their specific needs and threat model, balancing security strength with factors like performance, key size, computation speed. You might use level 1 for less critical applications, but level 5 for protecting top-secret national security data or critical infrastructure. It provides a clear, risk-based roadmap for adoption.
Okay, so the standards are emerging, but standards are one thing. Getting everyone to actually use them is another. Are governments and industries actually starting to move? Are there mandates coming down the pipe in 2025 to force this transition?
The urgency is definitely translating into action, yes. We're seeing real movement from governments and regulatory bodies. For instance, CISA, the U.S. Cybersecurity and Infrastructure Security Agency, issued guidance in May 2025, strongly urging federal agencies to start incorporating requirements for PQC into their new IT contracts and procurements. That's a powerful lever to start shifting the market.
Building it into the buying process. Smart.
Exactly. And even more significantly, there's the update to the Commercial National Security Algorithm Suite, known as CNSA 2.0. This is the set of cryptographic algorithms approved by the MSA for protecting U.S. national security systems, classified data, military communications, etc. CNSA 2.0 explicitly mandates the transition to PQC for these critical systems. The deadlines vary depending on the specific application, but generally fall between 2030 and 2033. Importantly, though, CNSA 2.0 states that PQC algorithms are the preferred standard starting as soon as 2025 for new deployments. These kinds of mandates send unambiguous signals to industry. You need to invest, you need to develop products, you need to migrate. It creates a clear market pull.
And we saw that reflected in the investment trends, right? You mentioned funding for PQC startups surged in the first half of 2025, even overtaking quantum software.
Absolutely. The venture capital and corporate investment communities have clearly taken notice. We saw significant funding rounds for PQC-focused startups. Companies like Accenture making strategic investments in firms like Quesecure, which specifically offers software and services to help organizations manage this complex migration process, things like discovering where vulnerable crypto is being used, crypto inventory, and implementing the new PQC algorithms.
But this migration, it sounds like a massive headache for organizations.
Yeah.
Decades of old systems, everything interconnected.
Oh, it's a monumental challenge. Make no mistake. We're talking about potentially ripping out and replacing cryptographic infrastructure that's been deeply embedded in systems for decades. The hurdles are significant. Legacy systems, dealing with old hardware and software that might be difficult or impossible to update. Interoperability, ensuring new PQC systems can still talk to older systems during the transition period. Performance overheads. Some PQC algorithms have larger key sizes or slower performance than the algorithms they replace, which could impact system efficiency. Workforce training, retraining IT staff, developers, security professionals in entirely new cryptographic concepts and protocols. This isn't just a simple software patch, it's a fundamental shift in cryptographic paradigms requiring careful planning and execution.
So what's the recommended approach? How should organizations even start tackling this?
The consensus advice is to take a risk-based, phased approach. Step 1. Inventory. You can't protect what you don't know you have. Organizations need to conduct a thorough inventory of all their cryptographic assets, identify exactly where algorithms like RSA and ECC are being used, what data they're protecting, and how long that data needs to remain secure. Step 2. Prioritize. Based on the inventory and risk assessment, especially considering data sensitivity and required lifetime, prioritize which systems and applications need to migrate first. Focus on the most critical and long-lived data. Step 3. Plan and migrate. Develop a detailed migration strategy, testing the new PQC algorithms for interoperability and performance impacts. Implement the changes in phases, likely starting with less critical systems or new deployments. Aim for cryptographic agility designing systems so that cryptographic algorithms can be swapped out relatively easily in the future if needed. It really is this massive global multi-sector effort involving governments, standards bodies, industry, academia, all working together to mitigate a future threat. It's transformed PQC from a purely theoretical concern into a very real present-day business and security imperative. For you listening, especially if you handle sensitive data or work in IT or security, the message is clear. The clock is ticking. Understanding PQC and starting the planning process is becoming essential.
Okay, we've covered a ton of ground. The hardware race, the corporate strategies, the incredible potential, the looming threat, the security response, which brings us back to the fundamental question, the one that's probably been nagging at everyone. How far are we, really, from quantum reality? You've made it clear it's not like flipping a switch, not one single moment. So what does this all mean? How should we even define quantum reality, given everything we've discussed?
That's the million-dollar question, isn't it? And you're right, quantum reality isn't a single finish line. It's much more like a series of milestones, different phases of capability and impact. To really talk about timelines, we first need to be clear on that crucial distinction we made earlier, the difference between a physical qubit and a logical qubit, remember?
Right, physical qubits are the actual hardware bits, the noisy, error-prone ones. Logical qubits are the stabilized, error-corrected abstractions you build out of many physical ones using QEC.
Exactly. Physical qubits are what we build. Logical qubits are what we need for reliable, complex computation. So when people talk about quantum reality, they often mean one of two key things, or maybe a combination. One is the ultimate goal, a fault-tolerant quantum computer, FTQC. This is the kind of machine Google is laser-focused on. And FTQC is designed to operate correctly despite the underlying noise and errors, thanks to robust QEC. It would be capable of running very large, very deep quantum circuits for long periods, enabling those truly revolutionary algorithms like Shor's for code breaking or complex molecular simulations. IBM's definition captures it well: universal, adaptive, and modular. That's the dream machine. But there's another, more immediate form of reality, quantum advantage. This is where a quantum computer, even a noisy, non-fault tolerant one, perhaps working with a classical computer, can solve a specific, practical problem faster, cheaper, or better than the best available classical computer alone.
Okay, so FTQC is the ultimate destination, but quantum advantage is like finding useful islands along the way.
That's a great way to think about it. And the key point for 2025 and the near future is that this incremental utility, this quantum advantage, is already starting to emerge in specific areas, like we saw with drug discovery or finance examples. It's happening well before we achieve full fault tolerance. So quantum reality isn't binary. It's arriving in phases. We're entering the phase of demonstrable quantum advantage now, while the phase of widespread FTQC is still further down the road.
That makes a lot more sense.
Okay.
It's not all or nothing. But okay, let's talk timelines then,
Yeah.
especially for that big, scary one. The cryptographically relevant quantum computer, the CRQC that could break today's encryption. There seems to be a huge range of predictions out there. What are the experts saying, and why is there so much disagreement?
There is indeed a wide spectrum of predictions, and that uncertainty itself is a major factor driving decisions today. It creates what some people call the quantum risk decision paradox.
The paradox being,
The paradox is that organizations need to decide now whether to invest heavily in countermeasures like PQC migration based on uncertain future timelines. If you wait for absolute certainty that a CRQC is imminent, it will be too late, especially given the harvest now, decrypt later threat. But if you invest too early based on overly pessimistic timelines, you might incur unnecessary costs or deploy immature solutions. It's a difficult balancing act.
okay, so what are some of the timelines being thrown around?
They really vary. You have tech leaders like Google CEO Sundar Pichai, who has talked about maybe 5–10 years for practical quantum systems to emerge, though practical can mean different things. IBM, as we discussed, is targeting fault tolerance specifically by 2029, but they anticipate useful quantum utility or advantage emerging even earlier, perhaps about 2027. Looking at broad adoption across industries, many experts suggest that 2030-2035 timeframe is more realistic for when quantum computing becomes a widely used tool for certain applications. Then there's Q-Day, that day of reckoning for encryption. Some more aggressive assessments worry it could potentially arrive by 2030, driving urgency for PQC.
And specifically for breaking RSA 2048, what are the CRQC estimates?
Here, the range is particularly wide, optimistic or pessimistic, depending on your view. Surveys. Some surveys of quantum experts find a significant minority believing a CRQC capable of breaking RSA 2048 is likely or highly likely by 2030, around 23% in one survey. That number jumps to about 50% believing it's likely or highly likely by 2035. More conservative models. On the other hand, you have studies like one from NTT Research in Japan, which use historical data and modeling of technological progress. They predicted with 95% confidence that RSA 2048 would remain safe until at least 2039. That's a very different outlook. Government targets. The UK government, for instance, has set a strategic target of having quantum systems capable of outperforming conventional supercomputers for key tasks by 2035.
Wow. 2030, 2035, 2039, that's a big spread.
It's a huge spread. And what's fascinating here is these timelines aren't just abstract technical forecasts. They are becoming strategic drivers. They influence government policy, R&D funding priorities, corporate investment decisions, and crucially, the urgency level felt for PQC migration. The uncertainty itself forces action. Because of the harvest now, decrypt later threat, organizations can't really afford to bet on the most optimistic timeline for encryption safety. They have to consider the possibility of earlier arrival. This inherent unpredictability, this constantly shifting horizon based on potential breakthroughs in hardware or algorithms. It's a defining feature of quantum computing right now. For you listening, it means the future isn't some single fixed point you can aim for. It's more like a rapidly approaching wave, maybe with multiple crests.
Yeah.
Understanding the range of possibilities, the associated risks, and the motivations behind these different timelines is key to navigating what's coming. #tag outro.
Well, what an absolutely fascinating journey this has been. A true deep dive. We've really explored 2025 as this pivotal year, the year the UN recognized quantum science, marking our firm arrival into the middle game of quantum development. We've looked at the incredible roadmaps from giants like Google and IBM, aiming for fault tolerance around 2029, but taking such different paths to get there. We saw the diverse hardware race from superconducting and trapped ions to photons, neutral atoms, and Microsoft's unique topological bet, all pushing the frontiers. And we really grappled with that profound dual nature of quantum, didn't we? The revolutionary promise to transform science, finance, AI, logistics, set against that stark existential threat to our digital security, which is forcing this urgent global race toward post-quantum cryptography.
It's become incredibly clear, hasn't it? Quantum computing is absolutely no longer a question of if, it's purely about when and how. We've genuinely moved beyond the era of just noisy prototypes. We're in a phase where practical utility quantum advantage is becoming tangible, even if that ultimate goal of full fault tolerance is still, maybe 5 to 10 years away for widespread use. This really feels like a point of no return, not just for the technology itself, but for everyone else too. For you, understanding these shifts, grasping the implications, it's becoming crucial. Whether you're thinking about investments or how to secure your company's data or planning future strategies, or even just wanting to stay informed about what might be the next truly massive technological revolution. The strategic calls being made right now by governments, by corporations, even by researchers, they are actively shaping the quantum-powered world we're all going to be living in.
So we want to leave you with a final provocative thought to maybe chew on or explore further on your own. Given all the rapid, diverse, and frankly sometimes contradictory advancements we've talked about today, and given that really tricky quantum risk decision paradox, the need to act despite uncertain timelines for a code-breaking quantum computer, what single action do you think is the most critical, the most important thing for individuals and for organizations to take right now, today, to help shape or at the very least to prepare effectively for this unfolding quantum future? This deep dive, as always, is just the start of the conversation. It's the beginning of your exploration to this quantum reality that, as we've seen, has well and truly begun. Thank you for joining us on the deep dive.